Yes. All right, welcome back. So we are starting our set of lectures about the detector technologies, and we are happy to have Yulia Furletova from Devs Lab, who is going to give us the two lectures.
Before I start, guys, I would like to understand your background. Do we have students here who have already knowledge in experimental physics and detectors? Or you all one, two, three, five. Okay, five. That's already great. Okay, so my goal today is to link actually physics to real hardware, which we are going to build, like real detectors, and see, what kind of technology we need actually to build detector, ESC detector with you guys. Yeah, and I will show you what was our motivation for certain technologies and why we decided, on that. And I think for those who do not have a background in, experimental physics with detectors, that will be a good set of slides where you can grab the information. So, just like disclaimer. So for materials for those slides, I use, like efforts from our yellow report, various ESC projects and proposals and collaborations. So I would like to right away thank all the contributors and my colleagues. And I, some of them you will see names on the slides, but some not. But I just would like to thank all. So here's outline. Very brief, description about ESC physics. You probably will know it up to now already, everything. But I will focus on the kinematics and then go one by one about what kind of instrumentation we have and why and how to actually link them all together. But we start with the accelerator. Because, when you build a detector, you have to understand what kind of machine you're going to use, right, for your physics. And you will have two lectures by Sergey and Christoph. Jumping at how to go back. How to go back. Okay. So we are going to talk today about the ESC. And at the ESC, we are going to, so those accelerators are based on the existing RIG facility. So that means we operate with protons up to 275 GeV. So we have to know the range of the particles. So the range is from 41 to 275. And we are going to use the existing facility, but we are adding on the top the electron accelerator, so in the same tunnel. And the range of the electrons will be from 5 to 80 G. So that is corresponding center of mass energy, roughly from 30 to 100. What is really important that we are going to have very high luminosity collider. They will have 25 millirad crossing angle. This is really important when you build a detector around this. It will be located at AP6. So if you just look at the ESC as a clock, so it will be AP6. And what is really important for the ESC physics, we need to have the forward instrumentation. And this is, relates to how you interact between the accelerator and the detectors and how you build together this instrumentation. Okay. Before we start, because you're all students, I want to give you some homework question. Maybe you can do it right away and calculate. So, why the collider? Why not a fixed target? You can say the JLab, we have fixed target, accelerator. Why don't we, upgrade it a little bit and use this? So try to calculate what kind of center of mass energy we will reach with EIC with 18 on 275, and try to calculate what will be the electron energy if we would like to obtain the same center of mass. I think for you it's very nice calculation. Probably you will have results, do not look at my backup slide because there is an answer to this question, but I think will be fun to do this calculation. But as you can see immediately from those pictures, you see that the kinematic of the events is very, very different. In the collider experiment, you have particles going 4 pi, like everywhere. While in the fixed target, it is mostly boosted forward, right? Because you're like hitting the beam. And this is what you have to consider when you build the detectors, around the interaction region. Of course, before starting building the detectors, you have to have collaboration because you cannot build this alone. Yeah, you need a team of the people. So right now we went through the painful process of the collaboration formation, but right now the collaboration is formed, and we have more than 170 institutions from 24 countries and 500 plus participants, and they're actually growing every day. And we have, many institutions applying to be a member of this cooperation. And you can see our spokesperson and deputy. So this is the sort of the history how the formation of the EIC and detectors get started. So we started in 2002. There was mentioning like white paper, mentioning also the long range planning, very dense document, more than 900 pages of yellow report. And I really, if you're interested in EIC, please read them. It's really, you will get a lot of information there. And there's not linked, but we also had the detector proposals in 2022. We had three detector proposals, and the one was selected as a project. If you ask the question, if the EIC is the first in the world deep inelastic scattering experiment, the answer is no. We have running at CBA, but there was another one, Hera, Daisy, where we actually, try to answer the question about the structure of the proton. But if you compare with what EIC is going to provide, so we didn't have polarized beam, hadron beam at that time, and the luminosity was really low, but a lot of discoveries. So let's, you probably already heard from Rosie about the introduction to the electron proton scattering, so I do not have to repeat this. I just wanted to mention that, for the EIC, it's really important to provide the coverage, XQ² coverage, and especially if people are interested in the transition area between the DIS and the photo production. So this Q², around 5 GeV. And actually also this ability, I mentioned there's different center of mass energies. So this will give you ability to, probe your protons at a different scale. And Q² is defined the resolution of your probe. And also testing the different, regions in X. Why also EIC is important? So we have actually the facility where we all in one, yeah. So we can focus only on inclusive processes where we measure only scattered electron. It's like the Rutherford experiment, and we can study the structure function. We can include also information from various particles, and we can study, I don't know, that heavy flavor production, for example, or we look at the exclusive processes where actually the initial proton is not really broken. So it's like a tomography, yeah. So you put a proton and you see, without breaking the proton, you see what is inside of it. In other words, why the EIC is sort of unique. So you can see, by the way, the main goals of the EIC in terms of the physics. But I just wanted to highlight on this plot. So it's a center of mass energy versus luminosity. I mentioned the JLab and CBAF. So as you can see, this is the only facility which can run at 10 to the 38 centimeter squares, whatever, luminosity. While HERA, which I also mentioned, we only was able to reach 10 to the 31. And EIC will be sort of in between, yeah? So it provides a good range of the center of mass energy, but, with reasonable luminosity. And what is really important, we need to provide overlaps between other facilities. And on this plot, you can see in XQ square plot, you see what is the coverage for the CBAF, what was the coverage for HERA, yeah, and coverage for the EIC in green. So this will be really unique so that we can merge the fixed target data to the HERA data and, of course, provide a lot of measurements with various polarization and nuclear beams. Before we start constructing the detector, I just would like to highlight that pseudo-rapidity is usually what physicists prefer to use when they describe the detector. They are not talking in angles, but they talk about pseudo-rapidities because they, with this number you can actually have more granularity in the forward and backward areas. Yeah, and let's start with the kinematics. So I mentioned that we need to, inclusive reactions, we need to measure the scattered electrons. It's one of the unique particles. So, and we just measuring the scattered electron, you can calculate x, y, and q square. And if you plot the, for the, certain energies of the beam, your isolines, let's say, you immediately see where the those particles are distributed in terms of the detector. Yeah, so high q square, high x events will be most likely in the barrel and hadron and cup, and low x and low q square will be in the far backward and electron and cup. So this will be sort of transition area between the photo production and TS. Also interesting to understand what will happen with the quark, yeah, and how the quarks are sort of distributed. And you immediately see the higher the energy of the quarks, they will be probing the high X region, and they are boosted in the hadron and cup and in the barrel. And of course, all the proton remnant also will be sitting in this area. So now let's look at the interaction region. So electrons coming this way, hadrons are coming this way. So this will be sort of the area dedicated for the central detector. As I mentioned, 4-pi detector, so we need to detect all the particles. And then what is really important that we I mentioned the forward instrumentation, but here the limitation are the following. So we have to deliver the beam, yeah. So there will be beam elements which deliver the beam to the interaction region. So we have to instrument this area such that we sort of detect all the remnant or particles going in forward area, and the same with the backward instrumentation. So low photo production, low q square events will be sitting over here. And of course, we need to design this detector such that it can operate with the different beam energies and high luminosity. That means higher radiation and background. So this is the central detector. So this is EIC detector, which we are planning to build. And I will go step by step with that. So now let's ask the question, which particles we need to detect, yeah? Because, you have to build the detectors, but you have to know what you have to build. So if you look at the particle data group. So we have 200 particles which are listed there. So you can see the discovery table. And for those particles which will be produced in a collision, so we have to measure momenta, charge, vertex, energy, and mass, particle identification. But we are lucky that only 27 particles can leave or can fly the distance before they decay of 1 micron, and only 13 particles can fly 500 meters. So for you to understand, 100 microns is the thickness of your hair. Yeah, so that means after collision, in a distance of the thickness of your hair, only 13 particles will survive. Yeah, will not decay. So, and we have to detect only those 13 particles, which is really good. So at least we do not have to worry about it. And so here actually the list of the particles which we have to sort of detect and worry, from the detector point of view. So we have to detect electrons, photons, hadrons, hadrons either individual or in a jet, muons, and neutrinos, and of course some neutral particles like neutrons and k-longs. So neutrinos, of course, we are not detecting, so they are only I think what we see in a detector is a missing PT. Muons will, so as you can see, they have different topology depending on what kind of detectors you're using or looking at, and we will go step by step. Let's start with particle with tracks and momentum measurements. In real life, tracks means those pictures. So I took them from internet, so you can see this. Someone left a track here, and the same in the particle physics. When particle interact with material of the detector, they are leaving some ionization in the detector, and they provide those those tracks. Yeah, this is actually a very nice pictures up to now. So it's in the emulsion. It's the resolution of those detectors for really right now we cannot reach this type of resolution. But the problem with those detectors was that it's you took the picture, you process it, you see the picture, and then you manually have to measure the distance with rulers. So we will need millions of students who can really understand and read those images. But of course, for real experiment, we need to use electronically recordable tracks, right? But right now I can say that even with most advanced silicon detectors, we cannot get the resolution which is really close to what was used, I don't know, 50 years ago. Yeah, for detecting the particle momenta, we need a magnetic field. That means we need a solenoid, yeah, or any other, magnet. And this nice formula which connects the momenta with bending radius in the magnetic field. So depending on what right on the left side, the particles will be bending, so we can calculate the charge. And those solenoids or those magnets, actually accelerators can work without them. So for them, it's even the pain, yeah? So they need to do the compensation and other schemes, but it's only the experimental sort of what experimentalists are using to detect. And we have to, of course, negotiate with accelerator team what are the strengths of this magnet we can use. Also, the dimensions of this magnet, it depends on if you are building the detectors from scratch in brand new facility, or you're going to reuse the existing infrastructure like halls, because you have to, if you build a really large solenoid or the magnet, maybe it will not fit into the hall or through the door. Yeah, so we need to see from all the aspects and how you will do the installation assembly. So, for example, are you going to assemble everything in the experimental hall, or you need to move this detector through the hall to the experimental area? And this is actually what defines your size of your experiment. Then a few words about how strong the magnetic field should be. We know that particles, when they are flying in a homogeneous field, the motion we call the helix, yeah, so they are like bending. And the higher the field, of course, the larger the bending radius, yeah, but it depends, of course, on what kind of momentum you're using. So if you have, for example, particles which have a lower momentum, like 1 GeV, in a strong magnetic field, they will be bended so strongly that they will fly inside the beampipe, yeah, and we will never detect them. While if we have too low a field and we have, I don't know, like 100 GeV particle, they will not be able to bend them strongly so that we will have the straight line in our detector. That means we will not be able to measure them. So this is the compromise, yeah, on like what is your physics, either, and you have to look at what kind of particle range you are talking about when you define the strengths of the magnetic field. At EIC, we are going to build a brand new solenoid. You can see the dimensions, so it's almost 3 by 3 meters, and with a 2 Tesla field. Yeah, you can see the how the uniform field is inside, and this is what actually defines the dimensions of the detectors, which you can sort of slide inside the bore of the magnet. Now let's talk about and ask ourselves, like, why do we need the precision measurements for the particle momentum? And I chose the example of the D0, which decays to the pions and the kaons. So what if you, for example, take the Monte Carlo files and just plot the invariant mass of pions and the kaons, you will see nice delta function with the true value at the right mass of the D0. And this is what you will have in the ideal situation if your detector can really like precisely measure the momentum. But of course, we this is the reality is such that we have some momentum uncertainties. So, and this is really the question at what level of uncertainty is acceptable for the measurements. And you can see the difference in the mass spectra if you have momentum uncertainties of 0.5%, 3%, and 15%. So with the 15%, you like barely see the peak invariant mass peak of the D0. That means we can say that 3% we still can accept, but better have something better than that. How the resolution of the momentum is sort of calculated. So there is 2 components in it, and again, so here how it's so there is 2 components. One is related to the precision measurements of your detector, and of course the length, yeah, of your tracking system. Again, the simple formula And you can calculate, for example, using this formula, what kind of momentum resolution for the PT of 10 GeV we can expect with 2 Tesla field at 1 meter distance if our resolution of the tracking is 100 microns. Yeah, so do this exercise when you have a time. As you can see here, so this depends linearly on the transverse momentum of the particles, on the resolution and the length. Another parameter is the multiple scattering. And this is really important for the low momentum particles because you will see this effect much stronger there. And this relates on like how dense material, what dense material you are using. And sometimes it's really, this is our sort of one of the main worries always for the detector construction, how to minimize the material, and I will tell you in the second one. And this multiple scattering is actually when the particles is entering the material, so they start to interact with this material, and at the end it's sort of flying with on the different angle with different momenta, and this creates all sort of mess. And as you can see, this delta sigma over p not really depends on the momenta, so it's only factor of what kind of material you use. What is important to know that if you plot this multiple scattering versus this precision resolution curve, you will see, because you have to sum them squared, you immediately see that even so that you can like invest billions of dollars in getting really precise detector, you will never achieve, if your detectors is really thick and lot of material, you will never achieve this, precision you need, yeah? So you need to really work from both ends. So you need to minimize the material, to minimize the multiple scattering effect, and also work on the precision of your detector, yeah, to get, like, this is just an example, so it just for you to understand how that works. Okay, now coming back, I mentioned that for the tracking, particles need to interact with the material. This is formula of the interaction. So as I mentioned, so we need to have the electronically recordable hits or tracks. Those have to provide really good resolution for the space points. It's mainly important for the charged particles. They have to provide momentum measurements, so we need magnetic field, angle, primary and secondary vertices. They have to provide some separation for the multiple tracks, and I will show you example later on. This really depends on what kind of resolution of the tracking system you have. If possible, provide the particle identification, and of course, keep the material on the minimum. On this table, actually, you can see what are the requirements from EIC. So this is one of the table from the yellow report, and you can see what we are planning to achieve in terms of the momentum and the spatial resolution in different areas. What is actually important also for the detectors is to know how the particles interacting. So the charged particles, if you have the multiple layers, so they will interact, they will produce sort of hits with some energy deposition in each point. And then, you have to reconstruct everything back to the vertex to see what is the primary vertex of this event. But on the top, the photons are not producing such tracks, so they're either flying through the detector or they leave the all energy in like one spot, yeah? So that means if we are talking about operation in environment with a very high synchrotron radiation, your nice event will be sort of, let's say, covered with single hits from those synchrotron radiation photons, and then it will be really difficult for you to reconstruct the track of the particle. Also important to know that we need to understand what is the acceptable position for the closest detectors, because there will be a beam pipe. We need to deliver the beam, and right now it's a constant battle with accelerated team what kind of radius we can accept for the beam. What also I didn't mention, I think this is also important. I mentioned about like number of hits here and there in the tracking detector, but this really depends on what is your readout or integration time of your detectors. Because if you integrate multiple events, this will create a mess for the particle for the track reconstruction algorithms. So we need to minimize this readout time. So I mentioned the heavy flavor physics and how well we have to reconstruct the vertex. And at EIC, the radius of the beam pipe is 3 centimeters. That means we cannot place the detectors closer than that to the interaction point. That means, the closest detectors will be 3 centimeters away from the interaction region. And they have to provide the separation of the primary and the secondary vertices, by the order of 100 microns. So it's really challenging. That means the closest detectors to the interaction region has to have their highest content. With this, we can reconstruct the vertex. And 100 microns is the thickness of your hair. Let's few words about the beam pipe. You can see the EIC beam pipe. In order to minimize the material and minimize the multiple scattering, the central sections near the IP will be made out of the beryllium. But of course, there are some flanges which sort of will limit our acceptance, but we can use them for supporting our detectors. And also, the beryllium is not pure beryllium because we have to provide the cooling. We have to, cool these detectors, and also there will be some gold coating to absorb all the low energy synchrotron radiation. I don't have a time, so okay. And as you can see, it's tapered beam pipe because we have a crossing angle. We have to accumulate crossing angle. And so this is, installation of the detectors will be really tricky because of this asymmetry. I found this slide really nice because it shows like, well, okay, so we are building the tracking detectors, what kind of technology we can use, right, for our setup. I mentioned those nice photos of the particle tracks, good resolution, but they are not electronically recordable. So we are not using those tracking systems nowadays, even so that they are very precise. We are not even using the multi-wire chambers or the drift chambers or straw tube trackers nowadays because the resolution of those detectors are not as great. So nowadays, the silicon state detectors, silicon solid state detectors, and micro pattern gas detectors are coming sort of forward, and I will show you why. But before jumping to the EIC, I wanted you to compare the difference between the silicon detectors and the gaseous detectors, like MPGD detectors, with like few words, and you have the table with the data. So the silicon detectors are very expensive. Yeah, so you cannot build large size 2 or 4 meters long detectors made of the silicon. So it will cost you a lot, but they provide 1 to 10 micron resolution. Yeah. So from the other hand, the gaseous detectors, you can build large size, and they're like cost effective, but the resolution is about 100 microns. And also in terms of the material, multiple scattering. So the gaseous detectors, just a little bit of material, gas, while the silicon, it's solid state. So multiple scattering is really a matter there. And you can see actually, and you can see the different vertex detectors in various facilities, CMS, straw tubes, and for the Atlas, PXD detectors for the Bell. Yeah, so you can see that nowadays this is modern technology. For the EIC, we are going to use combination of the silicon tracker and micropattern gas detectors. Of course, the closer to the interaction region, we are going to use more precise detectors like silicon detectors. And for the large scale, large size, we are going to use gaseous detectors because they're cheaper to build, and they only they are providing the space points, but they are not really contributing too much to the reconstruction of the vertex. Tracking system, silicon detectors. You can see we have the detectors very close to the beam pipe, 2 layers. And then we have discs, which are sort of covering the end caps. And MPGD detectors, there are 2 outermost layers here and there. Yeah, okay. So I saw that I added a couple of extra slides, but maybe I will use the older version. Okay, the maps, we are planning to use the maps detectors because this is state-of-art technology. Nowadays, so at CERN, they will mostly use 180 nanometer CMOS imaging technologies, but we are planning to shoot for 65 nanometers. You can see how those silicon detectors sort of operates. What is really important to understand, I really have it.
I see PowerPoint.
Okay, maybe, but okay. So there is a difference between there's different types of the silicon detectors. So we use those because they provide less material, and I will show you later on why it is that. But the main difference between the silicon detectors is how you do the readout. For the some technologies, you bump bond your readout on the top of your silicon detectors, and you can read out all the pixels simultaneously. So that means your readout is fast. You just one clock and you are reading all the data. But in this case, you have a lot of material. Yeah, particle has to go through the silicon detectors and through the readout. For MAPS detectors, they are using slightly different approach. So they are using the rolling shutter. That means they are reading like row by row, but in this case they are not introducing extra material on the top of silicon. But you have to pay for this. The readout time, because you're doing row by row, you can do the combination like 3 rows at a time, but it creates much longer integration time. That means you're like reading one row, you clear, then you go to the another row, and during this readout until you go to the first row again, multiple hits are complete. So again, a few words about the the material budget. So material budget, you can see this, what is radiation length. So only what is 0.0 for the inner layers, and traditional stave approach is like material and support structure for the outermost two layers. For the inner layers, as you can see, we are planning to use the bending or circular or round shape sensors, while for the two outermost is a standard stave. You can see the the like stave structure. Also, the ITS3 right now working on stitching the sensors instead of using the single layer with multiple sort of dead links and without and any whatever non-sensitive like the areas. They are working right now on stitching together multiple silicone pads, and it's actually like equivalent of having a large area of the detectors. What else? Yeah, the resolution. What is the readout time is about 5 microns. I can remind you that the bunch crossing at EIC is 8 nanoseconds. And you can calculate how many bunches you can go, how many interactions will go through this time window. And we also, those detectors are sensitive to the synchrotron radiation. So we found also another problem when we started to construct the detectors that, for the, especially for the disks, we saw that, okay, we can use various sizes of our sensors, but after the discussion with vendor, they told the owner, no, we cannot produce like random size. You have to pick up the size and build your detector. So right now we are like rearranging our silicon trackers and using sort of the size which vendors recommended us to use. And again, recap. So curved, thin, very thin layers for the inner part, very close to the IP, and more conventional structure for the outermost size, and for the disk as well. So now let's switch to micro pattern gas detectors. Yeah, somehow it didn't show up the most latest. Okay, I will update. There will be a picture showing the multi-track event. So nowadays, the micro pattern gas detectors are one of the most commonly used detectors. They provide very good resolution, so about 30 to 50 microns, and they were developed in the 90s. And you can see that the like gem detectors, they have like 3 stages of amplification, and this is done via introducing some holes in a foil, and you can compare. So this is multi-wire drift chamber. So you can see the resolution of the track we have. So we actually compared this a few years ago. The resolution with multi-wire chambers and gem trackers like back to back, and this is the same track measured with 2 different chambers, and you can see, how precise the LGD detectors are. You can see the individual clusters, individual energy depositions of the particle light in the wire chamber. It just, only like, white area. So we are planning to use for the barrel 2 technologies, let's say, so that they are MPGD type. One is what we call the cylindrical micromegas. We inherited this technology from the JLab Class 12 design, and you can see how it is, in a real life, how it looks like. Special resolution of order of 150 microns, but they're quite large. Yeah, so I suppose it's outermost tracking layers, but the materials are quite low. For the other type of the MPGD detectors, micro RWell, we need the motivation was the following, that the PID detectors, I'm going to talk about them tomorrow, they need a very, very good resolution, or the space point in front of the detectors, and that's why as well as the angular resolution. So we designed those tracking layers such that they match the acceptance of the DIRC bars. You can see the DIRC bars here, and MPG detector sort of matching the acceptance, and they will provide very, very high resolution space point. And it will have the sort of like merged structure between the GEM and micro RWells. I think it will be good for in terms of the resolution and also for the chart sharing. Okay, what else I need to tell here? For the disks, the same technology as micro RWell. Disks are quite large, so we will have 2 disks on one side, 2 disks on the other side. It's almost a meter in the diameter. You can see the layout. So the readout is sitting on the outermost area, so that it's not interfering, giving additional material for the particles. And yeah, the design. And of course, this is really important to understand how we get the signals out. Yeah, so we place our detectors, but we need to put the power, high voltage cables, without cables, and they are quite thick, so they are providing extra material. And there was a lot of really effort put into the designing the special road for the services and how they go, so that they are not really impacting the performance of the entire system. Yeah, in terms of the performance, so you can see how many hits per rapidity we are going to have. You can guess why we have 25 hits for the low momentum particles. Anyone know the answers? Right, because they are running the helix, and they are going along the beam pipe, so they provide multiple hits during their travel. But overall, there is about like from 6 to 7 hits per particle. And the resolution in terms of the momentum resolution and the vertex, quite good. Yeah, below 1%. And about, for the low momentum, it's about 50 microns, and well below that for the high momentum. So let's now switch to the colorimetry. So we have already our tracking system. We know how to measure momentum. We know how to measure vertex. We know how to measure charge. So now we need to measure energy, of the particle. For that, we are using colorimeter. And now we want to ask our question, like, why do we need the colorimeter at all? Because, you can say, okay, we have this formula. If I know the momentum and I know the particle type, like I can calculate the energy. Yeah, what is the deal? But first of all, not for all particles, the the type. Yeah, it's not always possible to identify the particles. And secondary, not all particles you can measure momentum very precise, or it's maybe not even possible. Like for the photons, you're not measuring momentum. And then you have to compare the resolution. So this is just an example showing, we discussed like that the tracking resolution has the dependence on the momentum, while the colorimeter, they have 1 over square root of E, so this sort of curve. And as you can see, depending on where they intersect, you can say, okay, for up to 40 GeV, I'm using the information from the tracking system because they provide better resolution. While for the higher energy particles, it's better to use the information from the colorimeter, while my tracking is really bad. Yeah. So, and this is how you sort of identify for your detector. You actually create such a plot, and then you immediately see what type of the colorimeter you have to use, because maybe, you know, if you want to have more precise measurements, you can start even at like 10 GeV. Lead tungsten will provide you much better understanding of the particle momentum. So this is your choice. Yeah. And of course, for the neutral particle, as I mentioned, for the neutrons and like gammas, photons, the colorimeter is the only way to detect them. Yeah. We need the colorimeter. So in nuclear particle physics, when we talk about colorimeters, we refer to the measurements of the energy of the particles. Yeah, and this is a very destructive process. That means all particles are completely stopping in a colorimeter, so they are not flying away. Unlike for like tracking detectors. Yeah, so in tracking detectors, you know, particles go through, they leave a little bit of the energy. But in the colorimeters, when they enter the colorimeter, so they are stopping there. This is the way how we actually measure the energy. Yeah. Only a few exceptions, muons and neutrinos, as I showed you before, they can, like, you know, penetrate through the colorimeters with the minimal interactions. So that means the colorimeter will be the outermost detectors, right? Because, you know, after colorimeter, the particle is gone. Yeah. And of course, colorimeter provide measurements for the charged particle and for the neutral particles, while tracking detector mainly for the charge. There are two types of the sort of colorimeters, or the way how particles interact with material of the colorimeter. And this is how we sort of separate. We separate electromagnetic colorimeter or electromagnetic cascade and hadronic particles and hadronic cascade. So for the electromagnetic cascade, so this is mainly electrons and the photons, quite high energy, because as I mentioned, like synchrotron radiation, that's also photons, but they are much lower energy. They are keV energy. And this, we are talking about high energy particles. So they started to interact with the material. They produce cascade of the secondary electrons and the photons. The main process is Bremsstrahlung and pair production. And as you can see from this plot, like, you know, one particle is entering and then it's starting to multiply, and the energy of the secondary particle is going to be decreasing. And at certain point, those particles do not have enough energy to produce the secondary, so the shower started to sort of end. Another important parameter is the radiation length. I mentioned this already. It's the way how the electron loses the energy, and probability for the photon to pair produce it's about 7/9. While for the hadronic cascade, it's completely different. It is also a similar technology, but you know, they have two sort of showers. the electromagnetic shower, which I just described, and also hadronic shower with, strong interactions. And usually it's, we are, when we discuss about the hadronic calorimeters, we are talking about the sort of interaction lengths. This is refers to like how deep your hadrons goes inside the material before the strong interactions actually happen. And if you compare two electromagnetic and hadronic cascades, you will see that the electromagnetic shower is much narrow and much more compact, while hadronic shower is much broader and and on this table, actually, you can see in terms of the comparison of the different materials, in terms of the radiation lengths and interaction lengths. For example, in order to detect hadron with, 100 GeV hadron, we need order of 10 interaction lengths. So you can, looking at these tables, you can multiply this by 10 and you immediately will see how many meters of the materials you need, right? And of course, you will see that for the liquid argon, you will need 9 meters in order to stop the particles, while with uranium, you just need 1 meter. So this is the way that shows you how thick your detectors will be. Apologies for the frame, so something that is a conversion. So resolution of the calorimeter. In the ideal case, it's proportional to the number of particles which they produce, and that's why in the resolution there is a term square root of E appears, but there is another terms related to material, like fluctuations, readout noise, and other stuff. For the EIC, I mentioned that the particles are flying 4 pi, so we need fully hermetic calorimeter. That means we have to cover actually from all ends. So we have the barrel, we have the end caps. We have the electromagnetic calorimeter sitting inside the solenoid and hadronic calorimeter sitting outside of the solenoid. And you guess why? Because we are using the thickness of the wall of the magnet for sort of as a pre-shower. And yeah, so you can see what kind of requirements for the calorimeters. This is an electromagnetic calorimeter. We are looking in the different areas. I mentioned that the electron and cup is mainly instrumented for the detection of the scattered electron, and that's why the precision, we need really high precision for the measurements. Barrel and the electron and hadron and cup are mostly for the hadrons, and that's why we can lose a little bit the resolution. I do not have a time, so you have to tell me what. 5 minutes, okay. Maybe I will just go through the electromagnetic and then we leave the hadronic for it. So as I mentioned, for the electron and cup, we are using lead tungsten. So this is the crystals. What is the fun things about this? That so you can see the lead tungsten crystals here, and also them arranged to the the matrix. Is one of the concepts at the Jefferson lab. And what is really important to understand, and we are looking at the experience from the CMS, that not a lot of really vendors can produce such good crystals. There is actually 2 in the world. And CMS, which also sort of is currently using the same technology. So for CMS, it took them 10 years to grow all the crystals. Yeah, and they are quite heavy. So if you just look at the 2 by 2 by 20 centimeters, it's just like almost 2 kilos. So such a small bricks, it's very heavy. So in order to grow, so they at that time they need like they had to produce 80,000 crystals and 2 days to grow. So we have to start in advance. That's why we are right now pushing for the early production phase so that we have a time to like grow and build those calorimeters before the accelerator will start operation. For the hadron and cup, we are using the tungsten sci-fi calorimeter. You can say like, why do we need the electromagnetic calorimeter in this area? Well, all your scattering electrons are going in the electron and cup. Why do we need electromagnetic calorimeter on this end? But you have to keep in mind that all like physics processes or the decay of various components like J psi will decay to the E plus and minus, and they all are boosted towards the hadron and cup. And we have to provide a good measurement. So the DVCS photons, so you can see they also have a distribution, so they will be detecting sitting in some fraction of them will be sitting also in a hadron and cup, and there are many other processes like pi zeros as well. Yeah, so we need the electromagnetic calorimeter in this area. So the total weight is 20 tons, right? You can see the resolution which was achieved was about 11%, which is good. And you can see it in terms of the production. So there's will be the tungsten powder embedded into the epoxy. So this will create like weight and material for the particles to interact. And then there will be the scintillating fibers. You can see the like arrays of the scintillating fibers going through the calorimeters, and then at the end of this tower, all the fibers will be connected to the slide guides, and at the end of the light guides there will be CPMs. And this will be identical to the star forward calorimeter, so we have the technology. For the barrel, this is actually very interesting. We need to have really good imaging capabilities, because all the jets, even so that the DIC is for low energy, but we would like to measure jet. We would like to understand the structure of the jet, and we are going to have the hybrid design. So hybrid means there will be imaging detectors, Astropix technology, sitting there, like sort of alternating with scintillating fibers and LED. So you can see how many imaging layers and LED sci-fis will be this section, and then will be the large area pure LED sci-fi. Yeah, so because we need to understand how the shower is developed. Yeah, another like closer look, this is like sort of shelf is Astropix silicon detectors. Right now they are developed by NASA, so we are collaborating with them, and the pixel resolution is 500 microns. So it will be really interesting. And for the LED sci-fi, the same technology as I just described for the barrel part, but the fibers will be arranged differently, so they will go sort of perpendicular to the particle tracks, and the resolution is about 5% to achieve. And this is a prototype which is very similar to the GlueX detector. I think I will stop here and leave the hadronic calorimeter for.
Thank you.
And question.
Questions to you then.
Anyone solve the
I already gave Reg.
Oh, okay. Okay. What was the energy?
About 10 tera electron volts.
Yes. 10 tera electron volts. So
Just under, it was nine and change.
yeah. And at JLab, I just remind that at JLab fixed target experiment, we operating with a 12 GV, not a TV with 12 GV, yeah. And in order to upgrade, we have to like increase by orders of magnitude, yeah. And this is really, we are right now debating on the increase of the operation by factor of 2, so from 12 GV to like 22 GV, and it's huge amount of investment. And 10 TV, it's, probably in your generation, or maybe your kids will or grandkids will be able to make fixed target experiments with such energy. But actually, there is idea of using the electrons from the collider, and the LHC, as you know, that they have TV energy electrons. There's a lot of proposal of extracting the electrons from the LHC and like shooting them on a target. This way we probably can operate. But this is probably will answer the question why we are building flight.
Whoever does the homework exercises may or may not receive a small token of appreciation. He has already, depending on the availability of those tokens. More questions?
Why aren't the segments of the barrel EM-cal angled? It seems like there's a chance that a particle could just go straight in between two segments without interacting.
Remind me which slide it is.
Yeah, right. This slide on the bottom right, it seems like the bottom right picture, it seems like a particle could go in between two different segments and not interact with the calorimeter.
So the fibers are along the like length parallel to the beam, and depending on design, how you like sort of instrument this, fibers, we are of course trying to make the gap small. This is the only like sensitive area. This is the sort of the areas which are capturing the light, which is produced by the interacting with the materials in there. But there will be a gap like at the edges between the barrel and like end caps, but we cannot avoid this.
Okay.
So this right now we are assuming that there will be like 10 centimeter gap because we need to pull all the services, all the cables from the tracking detectors, from the vertex detectors. So yes, there will be like some inefficiency, but we are trying to minimize it, keep it like at the 10 centimeter level. And yeah, but you cannot avoid this. Yeah, so just
And I presume that you pick quite carefully where that 10 centimeter gap is.
yes, absolutely. Yeah, because it's really depends like how your electronics is is arranged, and we would like to keep the as I mentioned the acceptance of various components like in the same pseudo rapidity gap, right? So that if we will lose like tiny pseudo rapidity gap, and the rest will be sort of covered by all type of detectors.
Any other questions?
I have a follow-up question. Since this is a school, on your first question of the center of mass energy, you said it's more difficult to get to higher energies with the electron. So why is it that we can get multi-TeV GeV, multi-TeV protons, but she just told us that it's very, very difficult to get to even 22 GeV electrons? Or what's the highest energy electron beam people have ever built? Do we understand that? What do you think is the reason why you can't build electron machines at the highest, the same energy as the
Maybe I will
the
just
LHC?
keep this picture so that it can help you to answer this.
What happens when you like accelerate any particle? Charged particle, right?
radiates.
Radiation. Yes, and why is it different for, the charges are the same? Why is it different for protons and electrons?
Mass difference.
The mass difference. Yes,
The main reason is that, when you bend the electron, there is a lot of, synchrotron radiation is emitted. Each bend, we are losing a lot of energy. And and actually this is, you will hear from the talks by our accelerator colleagues that they are right now planning to use the special technologies for the refilling electron storage ring with new electrons in bunches. There's two reasons why we need to keep the energy at a certain level, and second, they are losing polarization. So in order to compensate this, we are sort of refilling or adding extra, dumping one bunch and replacing it. So for us, for the detector people, all the synchrotron radiation, and I will show tomorrow also the impact of the synchrotron radiation. This is really a nightmare. Yeah, so it creates a lot of trouble for the tracking detectors. It creates the refill of the bunch. It's also unclear how well it will be because every time when you replace the bunch, there is instability in the system, and that might also create the background. And yeah, but we have to regret it.
More questions? All right, they're ready for the photo. Let's thank. Before we go for our coffee break, let's go downstairs to the sculpture. Take a photo of the school. I'll go tell Melissa and Socorro, and they will join us there. We'll need to hire the official photographer. Can we get somebody? We'll need to hire an official photographer.
there will be people walking around. That's what we did last time.
You want to lead them and I'll.
Sure, sure.
Okay, follow up